Hi, welcome to Algebra 2 Common Core. Today in lesson number 7, we're going to expand on what we learned about in lesson 6 as far as dependent and independent events, and learn about some tests for independence that will allow us to use probabilities to decide if events are independent of each other. So let's take a look at the box at the top of your notes. We are going to be using two different tests to determine independence. If we want to know if events A and B are independent of each other, we can either use the test on the left side. The test on the left side uses our conditional probability. So if we find out that when we calculate the probability of A given B, that it's exactly equivalent to the probability of A, then that tells me that events A and B are independent. If that's not true, then the events are not independent and they'll be dependent. Likewise, if I had the probability of B given A, that would need to be equal to the probability of B in order for A and B to be independent. So I can use either version of that test. In the second box, I see that the other way to test for independence is to use a formula that we had a few lessons ago. If two events are independent of each other, then when we do the probability of A and B, it will equal the probability of A times the probability of B. If we calculate the probability on the left side and the two probabilities on the right side, and that product does not equal the one on the left side, then that tells me that the events are not independent. Again, they'll be dependent. So we're going to practice with both of these tests for independence today. Both tests work equally well. Sometimes it's just going to be a matter of which kind of probability we're given as far as which one we're going to choose to use. So let's start with example number 1, where it says a survey of 57 sixth graders was done to determine which subject was their favorite. The results are shown in the table below, sorted by gender. So we're looking at these subjects of math, English, social studies, and science. And on the left side, we see that we have rows for female students and male students. So the first question says, does it appear based on the data in this table that the preference for math as a favorite subject has dependence on a student's gender? Show the analysis and explain your findings. So I am going to first of all start out by calculating the probability of choosing math as a favorite subject. So that means that I'm going to look at the probability of math over the entire population of sixth graders. So math as a favorite subject was chosen 18 times out of all 57 students. So when I do that division, I'm getting 0.32. Now what I'd like to do is take a look at the probability of math given the fact that I am only selecting female students to talk to. So when I look at the row that represents the female students, because that's my given, I then look at the ones that selected math. So I'm going to say that the probability of math given female, 8 of them selected math out of the 30 females that we had to choose from. When I do that division, that's giving me 0.27. Let's do the same thing for male students. So we want to know the probability of math given that we have a male student. So I'm looking at the row of male students, and out of the male students, I see that 10 of them prefer math out of the 27 that could possibly be questioned. So 10 out of 27 gives me as a percent or as a decimal 0.37. Now, when I look at either of those conditionals, neither conditional is equal to the probability of liking math in the whole population. So we're going to say that since neither the probability of math given female nor the probability of math given male is equal to the probability of math, that tells me that these events must be not independent. So by not independent, I can go ahead and say that these events are dependent. Whether a student chooses math as their favorite subject according to this table seems to be dependent on whether I'm talking to male students or female students. So it seems as though math is dependent on gender. I'm going to even write that. Math, according to this table, is dependent on gender. Now let's go ahead and see if that's true for a different subject. In the case of B, is it true about social studies? So is social studies chosen as a favorite subject dependent on a student's gender? So I'm going to do the probability of choosing social studies out of the whole general population for this 6th grade class. How many students chose social studies? There were 19 out of the 57 students who could have been selected. So that means a third of the students chose social studies as their favorite subject. Now if I then do the conditional probabilities of social studies given female, again I'm going to look in the female row and say of those females, of the 30 females, 10 of them chose social studies. So 10 out of 30 gives me exactly the same probability of 1/3. Let's do the same thing with the male. So let's take the probability of social studies given that you are a male student. I'm now looking at the male row and saying how many of them prefer social studies. That's looking like 9 out of the 27 males that were questioned. So I see that that also gives me a probability of 1/3. So in this case, it turns out that gender and social studies are independent. It didn't matter whether I asked the boys or I asked the girls, I got exactly the same probability of liking social studies. So that tells me that those are independent events. In fact, with this example, we really would have only had to show one, that social studies given female or social studies given male matched the probability of social studies across the whole population. If it works for one gender, it's going to have to work for the other gender, just based on the numbers in our table. Looking at this new table, a new two-way frequency table in example number 2, it says I've got male and female students in an after-school athletic program. So we can look at the numbers and we see that this is a hypothetical 1,000 table. So it's as though I asked 1,000 students and this is how many of them would have answered in all of these different ways. So the first thing I want to do is find the probability that a randomly selected student does participate in after-school activities. So I'm going to say the probability of after-school activities would be equal to, again I'm looking at the whole population, so there were 400 students who said that they participated in after-school activities out of my hypothetical 1,000 students that we could have questioned. So that means that that probability as a decimal is going to be 0.4. Now let's do exactly the same thing that I did in the last one. I want to know the probability of athletics given that I have a female student. So we're going to look on the female row. Now in the female row, the students who participated in athletics were 232 out of the 580 females that were involved in the study. So when we do this division, we're getting an answer of 0.4 as well. So because we see that those two answers match, I can go ahead and say that these events are independent. Now, just to see for the males It has to work out the same for the males if it worked for the females. So for the males, I'm going to say what's the probability of them being involved in an athletic program if they are male. Looking at the male row, I've got 168 that participate out of my 420 males that are part of the group. That also gives me 0.4. So because both of the conditionals were equal to the probability of just being in an after-school athletic program, that tells me that these events are independent. So for both of these first two examples, I used the first test for independence. So that's the one that says that the conditional probability, in this case, either of the genders, was equal to the probability of just being involved in the athletic program, regardless of whether you were male or female. So when they match, that tells me the events have to be independent. It didn't matter whether I picked a girl or a boy to ask. So looking at example number 3, I'm looking at a two-way frequency table that shows the proportions of a population that have given hair and eye color combinations. I'd like to try our second test for independence on this problem. So I'm going to say, we want to know whether the events of having green eyes and red hair are independent or dependent. And in fact, this question says we want to show that they are dependent. So let's start by doing the probability of having green eyes and red hair. So P of green eyes and red hair. I'm going to look in my table and say, where would I find that in my table? Here's the green eyes, here's the red hair. So I am looking specifically at that number right there. You'll notice that my table is a population proportion table, so it's already giving me the probability. So I'm going to say that this one is equal to 0.15. Now let's go ahead and find the probability of having green eyes. When I look for the probability of having green eyes, I see that 0.25 is going to be the probability of green eyes. Let's do the probability of having red hair. So the probability of red hair, so looking at my total red column here, this one right here, that probability is going to be equal to 0.18. Now when I multiply those together, so the probability of green eyes times the probability of red hair, so in this case 0.25 multiplied by 0.18, that answer gives me 0.045. So you'll notice that this answer for the and this answer for the product of each individual ones, they do not match. Since those do not match, that tells me that these events are not independent. If those two numbers did match each other, then we would say the events were independent. So in this case, if they're not independent, they have to be dependent events. And again, we use the second test for independence this time. Let's read over example number 4. There is a 34% chance that a person picked at random from the adult population is a regular smoker of cigarettes, and an 18% chance that a person picked has emphysema. If the percent of the adult population that are both regular smokers and suffer from emphysema is 14%, is being a smoker independent of having emphysema? So you'll notice that this one asks whether I've got independence. The previous one asked, were they dependent on each other? So I'm going to write down the probabilities that I'm given here. So the probability of having a smoker is equal to 0.34. The probability of a person that we ask being a person with emphysema, I'm going to abbreviate emphysema there, is equal to 0.18 because it's 18%. And the probability of being a smoker and having emphysema is equal to 14%. So when I take each individually, this is a nice easy one to do by that second test for independence again. So when I do the probability of having a smoker multiplied by the probability of having emphysema, so 0.34 multiplied by 0.18, in this case I'm getting an answer of 0.0612. So again, I see that these two numbers do not match. So if those two numbers don't match, I'm going to use 3 dots to stand for therefore. These events are dependent. They're not independent. The last example talks about a credit card company, and they say that 42% of their customers are classified as long-term cardholders. 35% pay their bills in full each month, and 23% are long-term cardholders who also pay their bills in full each month. Let the events that a randomly selected customer is a long-term cardholder be called L. The event that a randomly selected customer pays his bill in full each month is F. So let's read the words and just find all 3 of these probabilities. So the probability of having a long-term cardholder is equal to 0.42. The probability of paying your bill in full each month, that was 0.35. And the probability of both L and F being true is equal to 0.23. Now it says use the conditional probability formula to calculate P of L given F. So remember from 2 lessons ago, the probability of L given F is going to be equal to the probability of L and F divided by the probability of F. So substituting in these numbers, I've got 0.23 divided by 0.35, and when I do that division, that's giving me 0.657. Notice that it says round to the nearest thousandths. Now we're going to do our conditional probability to calculate P of F given L. So that's going to be the probability of F and L divided by the probability of L. So again, looking at our givens, I'm going to say 0.23 divided by 0.42. That's equal to 0.548. Now you'll notice that in order for these to be independent, I would have to have P of L given F would have to equal P of L. So when I look at these numbers, P of L given F is 0.657, but P of L is equal to 0.42. Clearly, they are not equal to each other. So right there, that tells me that these events must be dependent. They are not independent events. Just to be sure, for the second one, I'm going to say in order to be independent, the probability of F given L would have to be equal to the probability of F. So we know the probability of F given L is 0.548. And when we compare it with the probability of F, which is 0.35, again we see that they are not equal to each other. So this is another proof that these are dependent events. So I could have said that L and F are independent either by looking at what we wrote on the left side or what we wrote on the right side. Both of those tell me that they are dependent events. Thanks very much for working on tests for independence tonight. We're going to be doing a lot more work both in class and over the next couple days to see which test we should use when. Have a great night and we'll see you next time. Bye-bye.